Polygon angle sum theorem. Let's start with the warm-up. We're going to find the measure of each angle in quadrilateral ABCD. So the first angle, let's just go ahead and find the measure of angle A. Well, measure of angle A equals, looks like it's going to be the 32 plus 45, and if we take 32 and add 45 to it, we get 77 degrees. Now let's find the measure of angle B. The measure of angle B is equal to, well, already ready to go, 65 degrees. The measure of angle C, let's take 70 and add 61 to it. 70 plus 61 is 131, so the measure of angle C is 131 degrees. And the measure of angle D, 87 degrees. Now let's go ahead and work with number 2. I can see that ABD is a triangle. And in a triangle, the sum of the angles, sum of the interior angles is 180 degrees. So since I have 55 and 55, it looks like I have a total of 110 and I need 180. So 180 minus 110 would make the measure of angle A equal to 70 degrees. Measure of angle B, let's just add 55 and 30, that's 85. Find the measure of angle C, let's do that the same way we did A. We're going to take 30 plus 25, that gives me 55. And if I have 55 and I need 180, 180 minus 55 leaves me with 125. And last but not least, we have the measure of angle D. 55 added with 25 gives me 80 degrees. And so we were able to find the measures of angle A, B, C, D in both of those quadrilaterals. The objectives for this lesson are to classify polygons and to find the sums of the measures of the interior and exterior angles of polygons. Okay, let's start by talking about what a polygon even is. A polygon is a closed figure with at least 3 sides. Okay, probably didn't help much. Polygon, closed figure, okay, it's not closed. I've got this open angle, not a polygon. So the minimum number of sides I need is 3 so that I end up with this, well, closed figure. There's no openings to it. I can't, if I were standing on a piece of paper trying to get into the triangle, I wouldn't be able to because there's no openings. It's a closed figure. The sides intersect only at their endpoints. So notice they're only touching at their endpoints. I don't have like a crisscross or like almost like an hourglass kind of thing happening. I don't have this crossing. No adjacent sides are collinear. Well, that means I can't say here's a side and here's the next side, touching it. Same line, can't be collinear. When we name them, you start at any vertex, and then you either move clockwise or counterclockwise around, naming them in consecutive order. Okay, these are all polygons. These are not polygons. Well, this one's not a polygon because it intersects right there. And if that's not an intersection, if I'm trying to say, hey, these are 2 different sides, they're collinear, so that's a problem. This one isn't even closed. It's not a closed figure and intersects in more than just its endpoints. These 2 don't have segments for edges. They have curves. And this one's 3-dimensional and it has curves. So not polygons, polygons. All right, let's practice naming a polygon. Start with any letter you want, any of the vertices. I'm going to start with B. And this is going to be polygon, B, and then you can choose clockwise, counterclockwise, whatever you pick, doesn't matter, just make sure that you're doing consecutive. So you should be able to start on that vertex and then trace around the polygon in the order of the letters or the vertices you're going to list them off. So I'm going to say B, D, H, K, M, G, and then I'm back to D so I don't label it again. If I'm going to trace it, B, D, H, K, M, G, B. And I should be able to do that, even though I lift up my pen, I should be able to do that without lifting up my pen. So in the same order, or in consecutive order. To identify its vertices, well, the vertices are just the points that we just named. D, H, K. They can be named in any order. M, G, and B. Those are the vertices. The sides, those are segments. So I have DH, HK, KM, MG, and with a segment, it could be MG or GM, GB, and BD. So I have those 6 segments. So I've got 6 letters, 6 vertices, 6 segments, and I'm going to have 6 angles. So this is going to be a hexagon because there's 6 of those. The angles are angle D, angle H, angle K, angle M, angle G, and angle B. So since I have 6 sides, I said this was a hexagon. That's how we classify polygons, by the number of sides they have. 3 sides, triangle. 4 sides, quadrilateral. 5 sides, pentagon. 6 sides is a hexagon, that's what we just had. 8 sides, octagon. The most common octagon that you would see would be a stop sign. See them all the time if you're driving around, or if you're on the road, or if you're riding the bus, you see all these stop signs. Nonagon means 9 sides. Decagon has 10 sides. Dodecagon has 12 sides. Now 7's not in there. It's not used very often. It's a heptagon. When we get higher up, 22 sides, 48 sides, doesn't necessarily have a special name. We just can call it a 48-gon, or a 42-gon, or a 22-gon, or a 19-gon. So just the number of sides and then the word gon. Many sides, 19 sides, that's what we're dealing with. Okay, convex, concave, diagonal. To understand convex and concave, let's first talk about what a diagonal is. A diagonal is a line segment that connects 2 non-consecutive sides, so 2 sides that aren't already connected. In my quadrilateral, this is one of my diagonals, right through the center, or through the middle of my quadrilateral. I have 2 diagonals. Those are both diagonals. If I'm dealing with a pentagon, and if I've got this kind of pentagon, I actually have 5 of them, and they turn into, looks like a star. So my diagonals are just the line segments that connect non-consecutive sides. Now, polygon is considered convex if all of the diagonals, every part of the diagonal is on the inside of the polygon. It's concave if at least one diagonal or part of one diagonal is outside of the polygon. And they tend to be, they kind of cave in, so it's a good way to remember concave. It caves in, convex doesn't. An example of a concave polygon. That's a concave polygon. I have these diagonals. This diagonal happens to be completely on the outside. If any part of the diagonal is on the outside, it is a concave polygon. Even though you have diagonals on the inside, it just takes 1 point of one diagonal on the outside to make it concave. All right, we're going to classify the polygon by the number of sides and then identify it as convex or concave. So this star here has 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 sides. And if it has 10 sides, that means it is a decagon. And since, well, even though I have some diagonals on the inside, since at least part of one is on the outside, not whole diagonals on the outside, this is concave. So it's a concave decagon. All right, we're going to do an activity. Sketch polygons with 4 sides, 5 sides, 6, 7, and 8 sides. Then take those polygons and divide them into triangles. So for instance, sketch a quadrilateral, 4 sides. And we're going to divide it into triangles by picking one vertex, any vertex you want, and then drawing all the diagonals possible from that one vertex. So with this one, there's only one diagonal possible from that one vertex. Then we're going to count how many triangles we make. And in this case, 2 triangles. Well, I know with the triangle, the sum of the angles of the sum of the interior angles of a triangle is 180. So I have 180 degrees plus another 180 degrees to give me the entire quadrilateral. Well, 2 times 180 is 360. So I know the quadrilateral, the sum of the interior angles of a quadrilateral, or a 4-sided polygon, is 360 degrees. What we're going to do then is record all this information in a table, look for a pattern, so that if we need to find the sum of the interior angles of a 100-gon, we can do that without drawing the 100-gon, dividing it up into triangles, or drawing it and measuring all the angles and adding them all together. Okay. So, got the first one done here. I drew a 4-sided polygon, or a quadrilateral. Looks like a trapezoid. There are 2 triangles formed. triangle 1, triangle 2. And the sum of the interior angles is 360 because 2 times 180 equals 360. And we're using 180 again because the sum of the interior angles of a triangle is 180 degrees. All right, if there's 5 sides, pick one vertex, draw all the diagonals possible from that one vertex. So I've got 2 diagonals possible from that one vertex. Count the number of triangles, 1, 2, 3, and then find the sum of the interior angles by taking 180 times 3, or 3 times 180. And if you do that, 540 degrees. Okay, let's do the same thing with a 6-sided polygon or a hexagon. Pick one vertex, any one you want. Draw all the diagonals possible from that one vertex. Count your triangles. Take the number of triangles times 180, sum of the